We're moving now on to the second part of Lecture 3, Cavalieri and the First Integrals. The title of the talk is Integration of Powers and the Dawn of Calculus. Bonaventure Cavalieri was a Jesuit and a 17th century Italian mathematician who also was a contemporary of Galileo. He discovered how to calculate the integrals of x to the n for n equals 3, 4, 5, all the way up to 10. And he did this by using two inequalities, one which was larger than the integral and the other one which was smaller than the integral, and then taking the limit where the two approached each other, just like we did in the exhaustion method for determining pi. He employed the results for the sums of the powers of integers, and using that he could then take the limit where the steps in x went to 0 and the two inequalities approach each other, giving the limit which is equal to the value of the integral. He was able to explicitly do this for these first 10 powers, as we mentioned above. So how does this look? I have two figures here. The figure on the top is going to be corresponding to the lower bound. We're going to take the x-axis and break it up into a bunch of different intervals. In this animation, each time the interval is being divided by a factor of 2. And we're using what's called the left point rectangular integral rule. So we evaluate the function at the leftmost point in the interval, and because this is an increasing function, that gives a value that will end up being less than the integral. Now if we instead focus on the lower image, that one is going to give us the upper bound. It's the same rectangular sum, doing a rectangular sum for each interval, but we're evaluating it with a rectangle equal to the right point rectangular integral rule. So we're evaluating the function at the rightmost point in the interval, and that of course gives a value that's bigger than an integral, once again for an increasing function. Now if the integrand is a power of x, then this procedure turns out can be related exactly to the procedure of summing powers of integers. So we're going to illustrate now for you exactly how that's done. So we have a figure here that is showing once again that left and right hand integration rule. We have a blue and green rectangles, and the red curve is the one that corresponds to the power of k. So we're going to be trying to integrate in modern notation the integral from 0 to 1 dx of x raised to the kth power. We break the x-axis up into n steps with n plus 1 points. These are the points 0 over n, 1 over n, 2 over n, all the way up to n minus 1 over n, and finally n over n. So the lower bound then becomes the following. It's equal to the sum j equals 0 to n minus 1 of the value of the function on the left-hand part of that interval, which is j over n raised to the kth power. And then I have to multiply it by the width of the rectangle. The width of the rectangle is, of course, 1 over n. And I have to sum that from j equals 0 to n minus 1. And what you can see after I factor out the powers of n is that's equal to what we called sum underscore k of n minus 1. It's the sum of the first n minus 1 k powers of the integers. For the upper bound, we do the same thing, except we're now evaluating it with the right-hand rule. So instead of running from j equals 0 to n minus 1, we run from j equals 1 to n. And that turns out to be the sum of the kth powers out to the nth integer, also divided by n to the k plus 1. Now both of these bounds will approach 1 over k as n goes to infinity, as we can immediately see by checking the results that we got for k equals 1 and k equals 2, and I strongly encourage that you go back, look at those explicit values for k equals 1 and k equals 2, and verify that you indeed get this 1 over k result. All right, so let's summarize what was done here. Fermat was able to prove this result for all k using a different method. You're going to explore that on the homework. The book discusses some of the other issues that are required in defining what an integral is. In particular, the integral is well defined for any piecewise monotonic, which means strictly increasing or decreasing function. The book also discusses some additional subtle issues that one has to deal with in general, like the situation that's given in section 17 of the Toeplitz book. These kinds of odd situations usually do not play a big role in physics. It's important to know about them. There are things like Cantor sets and devil's staircases and strange attractors which do appear in physics, but in most cases we don't get these really odd things occurring in physics, and they tend to be more mathematical oddities that one should perhaps be aware of, but one usually doesn't encounter them in the work that you're doing. Now, one thing that the book really emphasizes, and I want to point out once again, is that the definite integral is not the area under the curve, as most people will say that's what the definite integral is. Often it makes sense to think of it as the total signed area under the curve, where when the function becomes less than 0, that area becomes negative.